Okay, I want us to look at the introduction to the PID controller design. Let me see if I can increase the size a little bit. Okay, in this tutorial, we will introduce a simple yet a versatile feedback compensator structure, the proportional integral and derivative, which is commonly known as the PID controller. The PID controller is widely employed because it is a very understandable and because it is quite effective. One attention, no, one attraction of the PID controller is that all engineers understand conceptually differentiation and integration so they can implement the control system without a deep understanding of control theory. And further to that, even though the compensator is simple, it is quite sophisticated in that it captures the history of the system through integration and anticipates the future behavior of the system through differentiation. Integration follows, but differentiation is supposed to predict. We will discuss the effect of each of the PID parameters on the dynamics of the closed loop system, and we demonstrate how to use the PID controller to improve the system performance. Then this is an area where MATLAB is key with the commands used in the tutorial, the transfer function, the step, the PID, the feedback, and the PID tuning. So in this content, we shall look at the PID overview, the characteristics of the PID, terms, the example or problem solved, then open loops, response, the proportional control, the derivative control, no, the proportional derivative control, the proportional integral control, then proportional integral derivative control, the general tips for design of the PID controller. Then we have a final automatic PID tuning. The PID overview. Okay, in this tutorial, we'll consider the following unity feedback system. You have the plant here. You have the reference signal. Maybe you can feed a test signal. In most cases, we put a test signal here. And we have a summer, which is supposed to get the difference of the reference to the output, and the error is being controlled and fed to the plant. So plant is a function of error. So normally a plant transfer function of an error. So the output to a PID controller, which is equal to the control input to the plant, is calculated in the time domain from the feedback error as follows. So the U of t is the proportional error, the integral error, and then derivative. Okay, first of all, let's take a look at how the PID controller works in a closed loop system using the schematic shown above. The variable E represents the tracking error. Let's reduce a little bit. Let's take a look at how PID controller works in a closed loop using the schematics. The variable E represents the tracking error, the difference between the desired output R and the actual output Y. So E represents the difference between Y and R. And this error signal is fed to the PID controller. This is a controller, the PID itself, and the controller computes both the derivative and integral of this signal with respect to time. The controller signal, which is U itself, the control signal. This is a now control signal. U into the plant is equal to the proportional gain Kp times the magnitude of the error plus the integral Ki times the integral, okay, again Ki times the integral of the error plus the derivative gain Kd times the derivative of the error. So there's a constant Kd and the derivative error, I think this Kd. Now, can make that changes later. Okay, this control signal, which is U, the control signal U, is fed to the plant and the new output Y is obtained. The new output Y is then fed back to the and compared to the reference to find a new error. So it is a continuous process. The controller takes this new error signal and computes and update the signal, the control input. So this kind of updating until the error is reduced to zero. This process continues while the controller is in effect. So the transfer function of the PID is found by taking the Laplace transform of the equation 1. So you have to take Laplace transform of this equation 1, and it will be Kp plus Ki of S plus Kd of S, which is equal to Kd squared plus Kps plus Ki over S. Where Kp is proportional gain, Ki is integral gain, and Kd is derivative gain. Thing here, they just multiply everything by S. You multiply everything by S, they divide by S. So if you multiply it by S and divide by S, so it means this one we're going to have S here. This one will have Ki S. Okay, and that's by S. So Kd squared, whatever the S will go and get the same. We can define the PID controller in MATLAB using the transfer function mode directly for this example. Supposing KP is 1, KI is 1, and KD is 1, then we can have the transfer function S and S. Then we have the control function, which is given by that. This is a okay. So it's allowed the C is equal to that or that, and this is how you can generate the function. You can generate the function with putting all these things equal to 1, because so that they don't give an error. So the transform is it is in the domain of S, the Laplace transform function. So the C now is Kp, we have S and Kd of S. So that will give you that kind of function in the MATLAB after declaring the values, and you'll have something of that kind. Alternatively, you can use MATLAB PID object to generate an equivalent continuous time controller as follows. You can just write C PID and put this in bracket, and it'll give you the same function with the KP, KI, and KD equal to 1. And that gives that information, because you will apply it, you'll use it all the same. Okay, characteristics of the PID terms.
Excuse me, sir.
Yes.
There are some members requesting to be added to the meeting.
Not mine. Thank you. What is it that the PID as a term or as a concept do to the system? Maybe you've come across that. Before we read it, I'll just give a summary because it will take time. So the KP the proportional gain KP has the effect of proportional increase of the control signal for the same level of error. It follows the error. So rise time, KP, rise time decreases, overshoot increases, then settling time, small change, and steady state error decreases. The diagonal part is supposed to decrease the rise time, increase the overshoot, increase the settling time, and decrease the steady state error. But the KD is number to small change at the rise time, decrease the overshoot, decrease the settling time, and no change to the error. So we say that the fact that the controller will push harder for a given level of error, it tends to cause the closed loop system to react more quickly, but also to overshoot more. Another effect of increasing KP is that it tends to reduce but eliminate the state error. Let me read that one. Another effect of KP is that it tends to reduce but not eliminate the state error. So it does decrease the state error, but can never eliminate it. Those who are coming late are really giving us problems. I don't know why. It's not good to interfere with the class when it's on. We say that the addition of the derivative term to the controller KD adds the ability of the controller to anticipate the error. It's supposed to know the future how the error is behaving, and they can predict. With a simple personal control, if KP is fixed, the only way that the control will increase is if the error increases. So if the error increases, the control will increase. With the derivative of control, the control signal can become large. With the derivative control, the control signal can become large if the error begins sloping upwards. Even while the magnitude of the error is still relatively small, this anticipation tends to add damping to the system, thereby decreasing the overshoot. The addition of the derivative of the term, however, has no effect on the state's error. So derivative, it reduces rest time, decrease overshoot, and decrease even setting time. You shall see maybe in the diagram. The addition of the internal term in the controller, which is Ki, tends to help reduce steady state error. In Ki, it reduces the exit error. If there is persistent steady error, the integrator builds and builds, thereby increasing the control signal and driving the error down. A drawback of this internal term, however, is that it can make the system more sluggish and oscillatory. It can oscillate, can be sluggish, slow, and start oscillating. When the error signal changes sign, it will take a while for the integrator to unwind that. So in general, the effect of the controller parameter Kp, Kd, and Ki on the closed loop system are summarized in the table below. Note, this guideline hold in many cases, but not all. If you truly want to know the effect of tuning the density of gears, you will have to do more analysis and you have to perform testing on the actual thing. An example of this is this problem that I think we have grown this kind of thing. We have a system, mechanical system, mass with the spring and also the dashboard, the forces acting, and the distance covered. Then the governing equation of this is given by this. The force is equated to the mass derivative and its derivative, the dashpot and its derivative, and the spring, this function, which is going to give us F. Taking the Laplace transform of the same will be this equation here. Then the transfer function between the input force and the output displacement x of s is then given by x of s over f of x is equal to 1 of this. So when m is 1, we can arbitrarily take values. Let m be equal to 1 kg, b be equal to 10 newtons seconds per meter, and k is equal to 20 newtons per meter. Then F is equal to 1 Newton. So, because X is what is supposed to be function level, take this kind of arrangement. Then the goal of this program is to show how each of the time Kp, Ki, and Kd contributes to obtaining the common goal. The first rise time, minimum overshoot, and zero steady state error. So there'll be this kind of action which is expected that rest time will be increased minimum overshoot, and zero steady state error. So in open loop system, they'll have this kind of thing. Open loop, there's no feedback. They'll have this kind of arrangement. The step function. The DC gain of the system is 1 over 20. By the way, if you divide everything here by 20, because to remove the constant and the numerator, so the gain up here will be 1 over 20. And so the DC gain of the plant is 1 over 20, so 0.05 is the final value. So 0.05 is the final value. So 1 over 20 is 0.05. This corresponds to the steady state error of 0.95, which is quite large, 95%. Furthermore, the rise time is about 1 second. Yeah, for it to rise to 90% of the 1 second, 90%, rise time is between between 5% to 90% of the whole process. So the rise time is 1.5. I think 95% somewhere there. And let's design a control that will reduce this rest time, reduce the settling time, and eliminate the shift error. So from this table shown from the table shown above, we see that the proportional controller KP reduce the rest time, increase the overshoot, the table, this table, KP supposed to decrease rest time, increase overshoot, small change over certain time, and decrease the error. So we say that from the table above, we saw, maybe if it is good English, we saw that the proportional controller KP reduces the rest time, increases the overshoot, and reduces the series error. The closed loop transfer function, therefore, of unity feedback system with the proportional controller is the following, where X of S is our output equals to Y of S, and our references R of S is the input. So this of this will give us this. So KP is, we had this kind of arrangement now. We bring in KP. In a closed loop, in a closed loop system, you'll bring in the KP. Let me just write something there for you a little bit. Maybe of the plant here, the controller, you know the KP. So we find that this one will, when you do the actual transfer function, this one will be up there also KP, and will also be added somewhere here in the constant. So that's why it is appearing at the in this manner. So the KP and the KP is being added to this function here. This KP up there and then added to this constant is a proportional gain. Let the proportional gain equals to 300 and change the M file the following. So KP is 300, C is equal to PD for the KP alone. Then feedback is C times P and 1. Then T is going to plotted between 0 with a step of 0.01 and from 0 to 2. Then you get a step of value of with respect to T and transfer function and T. So KP is that, then P is only a controller, then T is equal to 300 like that, 320, and the continuous time transfer function is going to be like this. So there's an increased overshoot compared to this value, increased overshoot. The same thing we're dealing with here. Increased overshoot, but decreased rest time. No, rest time was too long by that time, like open loop system. It was 1.5. But now rest time is reduced completely. Moves very fast, but has to go up beyond what is expected. And it will be undamped oscillation. Now let's now look at the step function. This is did I go very far? I think I went that far. I went too much down. Not really, not really. There's something I'm looking for. I'm seeing it here. Wait, just give me a time. Uh-huh. So good. So I went into somewhere now. So the bar plot shows the proposal to control that reduce both the rest time and the state test error. The error, the sweetest error, I don't know how I can explain it to you. You know, in a transfer function, let me just admit somebody here. You know, in a transfer function of the when you are testing the signal, let's say we have the final value, the step function there. Then it rises and comes there. This is still an error. It's not the error is reducing, but it's not meeting the goal. We are not meeting our goal. We cannot reach the goal. So this rise time, for me at somewhere here, is the rise time. It's not the rise time, but this is a transient state. This is a transient. But this other part here is the steady state. That's why we get the error. The steady state. This region is a steady state. And this region is a transient state. So this is the time function. Then this is the transfer function will be. And you can see that the KP has accelerated the transient state. Instead of it slow, it has become very fast. It has been accelerated. And also it has accelerated the steady state error. It has accelerated the steady state. The steady state has been accelerated. It has moved so fast. And it has given us this condition here. And the error, he has reduced the error, the steady state error. It's almost the line. But now, proportional derivative controls. I'll give you this. This is not a PDF. I just give you this site so that you can look at it at your own pace. The proportional derivative control. I wish they could have given us the derivative alone, first of all. Now, let's take a look at the PD control. From the table shown above, we see that the addition of the derivative control, KD, tends to reduce both the overshoot and the settling time. So when you look at this, KD, you reduce rest time, small change. It's not very, it doesn't affect that one so much. A small change compared to KD. But what happens here, this increase overshoot, but now we have to reduce it. Then settling time, it was small change, but now we have to reduce it. And no change for the set error. It remained the same. So we shall have a look like that now, proportional combining the derivative. In a closed loop system, we shall have this. And normally, these things are not, they are added, they are not in a parallel, they are a parallel kind of thing. The block diagram for PID, the block diagram for PID looks like this. The P, the I, and the D, they're in parallel. So they're adding up. You can join all of them and sum them up here. So if you're using P and D, we eliminate this one. So in this case, we shall have this one coming at the top, and this one is also adding the coefficient of the second term, 10, and there's a 10 here, so we can add the KD, and the KP is added here. It remains the same. This one is the one we are going to change. We are going to change the damping coefficient, and we are also going to increase the gain. So let's KP be equal to 300. KD equal to 10, and we are going to do the C, the controlling part is KP, theta, and KD, and feedback is this. Then transfer function, the timing is given from 0 to 2 with the step of 0.01. Then the step function is in that category. Then we have the control, the one we are saying that you can also put it as an element of we set up values with KP is equal to that, and KD is equal to that, continuous time PD controller parallel. In parallel form, we'll get that. Then when you do the analysis, you do the simulation, you find you have reduced the steady state. You have reduced the overshoot, and the rise time has been reduced completely, but overshoot has almost remained somehow. What about overshoot? Overshoot has decreased, but it does not be eliminated. Does never be eliminated. It has reduced. Now let's look at the proportional integral combined. So when we look at the proportional integral combined, proportional integral combined, these two, the first two, they have the same property in the rise time. Overshoot, they have the same property, but settling time, Ki has increased settling time, but reduces the error. So here the only problem is settling time, which has been increased. Let's see how it is done. Proportional integral control. Before proceeding to PID control, let's investigate PI control. From the table, we see that the addition of integral control Ki tends to decrease the rest time, increase both overshoot and settling time, and reduce the stress error for the given system. The closed loop system transfer function cover PI as follows. So you find that there's a 10s squared here again, and there's a function here which is coming up, and Ki here. Okay, there. So let's KP equal to 30 and K equal to 70, then create an F file. When you create an F file, you get something like that, then it's fine. We have increased rest time. It has gone beyond. It does not accelerate the steady state. It does not accelerate the steady, it does not accelerate the transient time, but it accelerates the what? It accelerates the cycling time. Yeah. Accelerate means that you reduce cycling time. You increase the cycling time. You fast track, you make it move fast. But the cycling time has been moved faster, has been accelerated here. And the thing has settled very fast. But even for sure, the only problem we have is transient. Transient. That's why you cannot use PI alone. The response to the system will be so slow. If it's a vehicle and it is supposed to, it does hit, bam, or that hit a hole somewhere. Okay, I'm sorry, the network is maybe caused a problem. I've just sent the the link for this notes I'm sharing with you. You have seen that when you use the PID controller, everything is settled completely, and you can go and see the general tips of designing a PID, and also read through all the notes and find everything working for you. Uh, Unless there's a question, I think we can call it a day for that matter. Anybody with an issue? Oloibe, Tony, are you? Oloibe, Sherry, Sherry Were,
I'm okay.
thank you for coming. Kimaiga, Rebecca, are you there?
I'm okay too.
Wow. Samuel Cho,
Yes, thank you, sir. I had a question. How are those parameters chosen for a specific system, the P, I, and the D?
oh yes, oh yes. I told the procedure. Did I read the procedure anyway? The procedure somewhere here. Procedure of site designing. Procedure, the tips. Just go slowly and read the tips,
Yes.
and from there we can discuss. There is no magic. It is just a matter of trial and error. You know, when you're designing a house, you have to start by putting measurement on the ground. But you've always seen that people move sticks so that they can get the accurate values. So you tune it based on the ground. So wengine unakuta mtu anaweka mawe somewhere so that you can lift the item so that the ground can be levelized. So it is a matter of just try and reduce everything. It is a tuning kind of thing, just like it is possible to for you to, as engineer, you are supposed to. That's where you come in. How do you? What is ability of tuning? So I don't want to say that if you want to get the damping factors to be some level, then you have to choose. But whichever you choose could be your best. But it's a very good question. Thank you so much. Like that. You know, okay, I gave you some, not assignment and such, but it was just a classwork. When I give you a classwork, just try to do it. There's no need of copying. I don't penalize you. I just want to see whether you understand it. But if there's something I want to give it for marking and recording marks, I'll tell you. This one is going to be used for recording. So when you're copying means that you fear that you're going to fail. So you have to copy from a friend. It will not help you. Just do it. When I mark, I'll tell you this one you're not done well. You can improve this. But no, our work shall be full of our work shall be full of doing exercise. Otherwise, if I don't give you exercise, it will be not good at all, at all, at all. Uh, Let me just give you some assignment here. looking for assignment for you. I'll send it to the class rep later on. So I don't need to hold you. So this time round we shall have a cut, but not take away. Choose a date for us. Talk to the class rep and choose a date for us for a cut one. It is something short enough, and just to I'll give you some kind of some of the questions will come from assignment I gave you, but not repeating the same, but just to test on whether you're doing assignment. The first cut I gave you, take away. It was supposed to present it maybe later, but we shall have a class of maybe 1 hour to do face-to-face cut. Thank you. Have a good day.